I would like to invite our next speaker, Lotfi Massarweh from Delft University of Technology. And he will be speaking about analysis of uncertainty information of real-time SSR corrections from a regional network and impact on PPP-AR.
Yes, thanks for the introduction. Welcome, everyone. Today we're discussing a topic that was also brought in a few weeks ago in a bar splinter meeting. This work is done together with my colleague, Dr. Brack at GFZ. For the sake of time, I will go to the agenda. So I will provide a very short introduction and I will describe the methodology for the mathematical definition of the network and the user model. And then I will basically provide an analysis of the real-time satellite correction, and I will focus really on the uncertainty of this correction and the impact on the user model. So let's start with a short introduction. We know, of course, that in general we use a network of stations in order to estimate correction. These corrections then are provided to the user. In this way, the user can basically take care of this satellite product and can perform precise point positioning or also enable ambiguity resolution at the user level. At the same time, we would like to investigate aspects concerning the uncertainty of this correction because they come from a certain estimation problem. So they are not deterministic, they are not perfect, even if in general they are treated as such. So when we look at a certain network, we will focus mainly on a regional network. In our case, this is quite a large regional network. So for instance, we have considered a European example. So it's actually continental-wise. You can see, just as an example, the visibility of a certain GPS satellite. So in general, the satellite is visible over the network over several hours, but this will not always be the case if we think a bit in the future with the evolution of a LEO PNT system, but we will not discuss this today. I will simply then refer in my conclusion, again, come back to this topic of the LEO PNT constellation in the context of network estimation of correction. So let's start with the methodology. We start generally with a simple formulation of the code measurement, first equation, and the phase measurement, assuming deterministic error are taken care. And of course, you see different parameters, geometric parameter like troposphere and the other component of this pseudo range and carrier phase measurement. But unfortunately, we cannot estimate directly this physical quantity, so we need to take care of rank deficiency, which means basically we are defining estimable parameter, and this estimable parameter allows us to provide a single solution, a unique solution in our model system. When we look at the network case, of course, this is a quite standard theory in the literature. We can actually define for the different, basically, parameter of interest, both at the network side, so the station side, but also the satellite side, the meaning of this estimable parameter, which are always marked with a tilde, so they are on the left side of the equality, and the right side actually define which are the interpretation of this correction. This is very important, especially once you want to analyze or understand how a change of datum or when you want to compare, for instance, a different network provider. What we will focus today, however, are simply the correction of the satellite, so especially the transmitter clock offset, and at the same time also the phase biases, because they together are enabling indeed PPP ambiguity resolution, together also with together of course with the code biases if necessary, but this depends also on the frequency used by the user. At the user level, of course, when we look at the formulation at the user level, you see that we start again with the code and phase measurement, the first two equations. And the moment we consider this red quantity, so the correction we apply to code and phase, of course, below you can see which is the actual physical interpretation of this correction. So this correction, which are de facto the estimable satellite clock with the tilde and the estimable hardware delay, actually have an interpretation which is a bit further, and this is again quite known from the literature, but the key aspect, of course, is that this correction, so the datum they introduce, it's not an issue because this is taken care in the formulation of the user model, and we always apply uncombined indifference for the network and the user case. But at the same time, the uncertainty of this correction is actually neglected, and this actually could be an issue then for the actual proper modeling and the optimality of the mathematical estimation for the user side. Let's start with analysis of real-time satellite correction. So basically, Andreas basically implemented this undifference and combined formulation. This was running actually for a week in real time, so it was meeting the real-time requirement from the provider side. The orbit and clock, actually the orbit were actually provided or predicted through an ultra-rapid prediction, so are not part of the estimation, but in the network estimation, the key quantity are basically the satellite clock and the satellite phase biases, because also the code biases, due to the stability, were actually corrected, so were not part of this real-time estimation. The clock and phase biases were estimated at 5-second sampling, and in this case specifically, we consider two constellation tool frequencies, so Galileo and GPS case. We all restricted to regional networks, so of course the issue is that the visibility of the satellite, we do not have all the satellites in common visibility. And from the user side, of course, providing information about correlation of all the satellites is actually large amount of information, which simply is not feasible, but also in terms of bandwidth that the provider should basically take care for providing this additional information, which now we are analyzing. So the question that we look at is which strategy might be really convenient, so it's a bit of a trade-off. To do that, we have a bit of a look inside, for instance, the uncertainty of a correction for a specific satellite. So on the left side, you see in black the actual correction which are estimated over the 24 hours over 2 passes of the satellite for clock and the 2 phase biases for the 2 frequency of the Galileo. Then on the right side, in the diagonal, we have the standard deviation, which you see is show how the correction converge. And then the diagonal term are actually the correlation, where you can see the correlation between the clock and the phase biases slightly decrease because the phase biases have a constraint in time, which are assumed to be constant, and then the clock become more prominent. In the moment we combine the correction, because again it's important, the combination of the correction we apply to code and phase, in this case to the phase measurement of the 2 frequency, you can see in the orange line that is actually the predominant term. This is what we really care to have a look at. And this is also the case, of course, if we look at a different satellite, which has a very similar passes over the same day. But most interesting, when we go to look at the correlation between the satellite, so once again, we have clock and the 2 phase biases for the 2 satellites I showed before, so the E03, E08 of the Galileo constellation, you can see the actual correlation is not really high. This is also known in literature, but we need also to be careful. This depends really on the model that has been used and the parameter that you're interested. So this is not a generic for any type of network estimation. This is referred to the model we apply and the regional network we are considering. If you look, of course, for all the satellites, you are interested in not this specific case, you can see in this very short video, actually, how the evolution, of course, of the correlation for intra-constellation or between constellations, so in the middle you have between the Galileo and the GPS satellite. In general, the correlation is actually very low. Is generally smaller than 0.3 in absolute value. Sometimes it can reach at 0.4, but in general, it's quite small. So this is a good indication of the idea, which now we have to look into, of actually neglecting correlation between the satellite, while we saw there is a very strong correlation intra-satellite, so between the different components we estimate for each single satellite. So at this point, we can have a look, and starting from this information, the full information, have a look at how this will impact the PPPR model, so in particular the user model. In order to do that, you could consider, for instance, observation. These are observations for all the satellite, and for all the satellite you get code and phase observation. In the moment, of course, you want to apply this correction through the matrix A. This is a block diagonal matrix because, of course, you apply correction for each satellite. So this is very important because if you neglect the correlation between satellites, actually we will not introduce any correlation then in the measurement, clearly simply because you apply each correction for each satellite. At the same time, the different correlation, this might propagate into the actual stochastic model of the user. So let's try to have a look, and what we will focus at, we'll only focus on the red term, so the contribution that comes from the uncertainty of the correction. We will not mix it up with the actual already uncertainty which is linked to the observation, and we will focus on the phase observation because those are supposed to be at millimeter level, but as you will see, this can be easily contaminated by the uncertainty of the correction. So I take an example in this case for the phase data. So I take, for instance, a user, and for this user, I compute the visible satellite of a certain elevation mask. And at that point, I can actually compute what will be, based on the current uncertainty of the correction, which is given by the provider, three different cases that you see in the three column when I consider a diagonal matrix, so I neglect any correlation or any correlation at all. At the same time, with the block strategy, actually, we neglect only correlation inter-satellite, so we only account for the one intra-satellite. And the full case actually consider the full information. As you will see, in some cases, the standard deviation is high, but this is just typical for the regional network because the satellite in view start converging. So you can see that if I move, for instance, in 5 minutes, these start decreasing because, of course, the satellites start converging. But the main aspect is to see how different it is from the diagonal case with respect to the other two, the actual standard deviation of the correction which are already propagating to the measurement, so will affect phase measurement. And this is very important because the orange line is actually, the orange bar, sorry, are actually the same for the block and full, because as I mentioned before, there is not a very big difference. At the same time, for the full case, we see that we also bring in the correlation between the satellite because we are accounting for that. And this play an important role. Of course, in the moment we move forward with the time, you see some satellite will enter into play, but the difference between accounting for the uncertainty without correlation and accounting the correlation intra-satellite, so of a specific satellite, it makes a huge difference in the stochastic model of the user. Now, to go a bit look, of course, from the provider's perspective, because this highly depends on the strategy then for ambiguity resolution, we could have a look at the single difference phase data, so between satellite, because that's usually the parameterization which allows then to have integer estimable ambiguity. So when I do that, you can see here, again, for the tree strategy, in the single difference phase data, where we take one pivot per each constellation, how already the diagonal case, so just providing some diagonal terms of the correction, or the uncertainty of the correction, introduce correlation. This is expected by the single difference operation, but the correlation is much more extended, of course, when you account already beforehand the correlation between the satellite. One important aspect you will see in all the three cases, the correlation between constellations here is very low. It's not perfectly zero, but it's very low. And this is due to the fact that the common data, common mode, actually simplify in the between satellite differencing per constellation that we do differently. So this is a key indication that this has a huge impact for the PPI user, but again, will depend on the PPI user strategy. So then for the user perspective, there are different options that we are actually now investigating. I think I'm right on the time, so I will move a bit to the conclusion. The key message that I would like to provide is that the uncertainty of correction, I think it plays a role. This role is not negligible if you want to go to a precise positioning, to very high accuracy positioning. I think at the moment there is not really format which allow that, and will not be feasible to provide a full variance of full information in the real time. But I feel that per satellite information of the uncertainty, this could provide very high benefit to the user. So it will be nice to discuss in the next Splinter meeting. And to conclude, a key aspect will be for the LEO PNT, because you will see there that the convergence of correction in the regional network is actually very slow, because the satellite in 10 minutes actually is over the network. So this will be quite an issue for the user that want to make use, of course, of this new constellation coming up. I think that's it. Thank you very much for your attention.